So good morning, welcome back. It's Friday of the fourth week of class. I realized we are almost halfway through this quarter. In some ways it feels like time is dragging. This is day 46 in quarantine. We actually have tally marks outside my little office door, just like I'm in prison or something like that. So it's day 46. But on the other hand, time seems to be flying, and I've just really enjoyed the chance to connect with you all here at 10 most every day. I know some of you are just here watching, others of you are participating in the conversations, but I enjoy seeing you in class, and then I've really enjoyed the assessment presentations on Monday. I know they're a bit stressful for all of you because there's understanding in what questions are going to be asked, but nevertheless, it's just been really cool to have that opportunity to interact and hear from you and hear how you're learning. And I've just been really impressed with how collectively you're working together, you're understanding, and it feels like, I know for some of you, this will be the last math class that you ever take, and it's probably one that you will never forget. I mean, you might forget how to work with infinite series, but you'll probably never forget the COVID math class that you took via Zoom and all of its crazy idiosyncrasies. So welcome back. We're going to talk today about another couple of tests. We're going to talk about the comparison test and the limit comparison test. This particular section I'm not quite sure whether it's long or short, but we've got a couple days scheduled for it. And so if we don't make it all the way through today, that's okay. We can spend a little bit of time next time, or maybe we can even use a little bit of our time on Tuesday to review and to see if everybody's on top of this series stuff. So when last we saw our intrepid heroes, we were learning about the integral test and the test for divergence. Test for divergence says that if the terms within the sequence don't go to zero, then the test must diverge. Pretty straightforward, doesn't apply very often. The integral test says if the integral that's related to the infinite series converges, then the infinite series converges. If the integral that's related to the infinite series diverges, then the infinite series diverges. Those are interesting. The real power that came out of that section was this little thing called the p-series. And the p-series is going to be powerful because it's going to give us something simple and easy to work with that we can compare to more complicated things. So today what we're going to do is we're going to introduce this comparison test that can take advantage of that p-series and also the geometric series that we've already worked with. So let's dive into our notes. All right, so this is the beginning of section 10.5 on comparison tests. And there's two of them. There's the comparison test, and then later we'll get the limit comparison test. So here's the test in words. So it says, suppose that the series of the ANs and the series of the BNs are series with positive terms. If BN is convergent, if the series of the BNs is convergent, and all the A's are less or equal to the B's, then the series of A's is also convergent. If the series of B's is divergent and the A's are bigger than or equal to all the B's, then the series of the A's is also divergent. What? Like, what does that mean? What's that saying? Let's look at a picture and see if we can understand what's going on. Okay. So here's the deal. So actually I should keep my color straight. Suppose we have this black series below that's unknown. And we're asking ourselves, does this one converge or diverge? C or D, converge or diverge? And we don't know. And what we do is we compare it to this series above that's known. Why is it that I'm so confident that the one above is known? What kind of series is this?
P series, and we could do the integral test.
Yes, it's a P series. What's the P in this case?
Power.
2.
Yeah, 2. P is for power, and the P itself is 2. Exactly, the power. So it's a P series, P equals 2. So that means that the P series does what? It converges or it diverges?
Converges.
Converges. I can't do this. Okay. So it converges. So we're saying that this thing above is converging. So it's approaching some limit. Let's call it maybe S for the sum. And that tells us that the black one that is below, which is underneath S, must also do what?
Converge.
So it must also converge. Why? Because it's stuck between 0 below and S above. We know that it's stuck somewhere in between there, and so it must converge. All the terms are positive, so we know it has to be increasing. And this actually ties back to one of the theorems in section 10.2, where it talked about the monotonic sequence. So since all of these terms are greater than or equal to 0, that tells us that the partial sums are going to be increasing. And because we have the red thing converging, we know that it's bounded. So we're saying that these partial sums are increasing and bounded. Therefore, by that theorem back in 10.2, we know that it must converge.
Dusty?
Go ahead.
If I'm looking at our definition of the comparison test, which one would we be calling A sub n? Yeah.
Good question. Let me
I'm having
covered up my notes on the computer, so I got to flip.
Okay.
So this is saying that this would be saying this up above, here's the sum. Oh, I've got to switch my colors. Here's the sum of the BNs. And so the sum of the BNs converges. All these ones below, here's the sum of the ANs. This is our unknown. And so since the red BNs in this case that are above converge, the black sum of the ANs below converges as well by the comparison test.
And the AN is smaller because its denominator is greater?
In the actual expression?
Yeah.
Yes, exactly. Yeah, so think about these terms, right? If you have K equals 1, you're going to get out 11. If K equals 2, help me out, 14. K equals 3, 19. Whereas up above, you're going to get out 1, 4, 3 is none. And so the addition in the denominator, so a bigger denominator, makes the fraction smaller, just like you said, Enrique.
Thanks, Dusty. The visual helped.
Cool. Other questions before we go to the other version of this graph? Very good. So here is another version. So in this case, here is our unknown. Lost the N. Unknown. Okay. And below, we have a known series. What kind of series is this one that's below?
I like to treat everything as P and say that's to the 1/2.
It's a P series.
Yeah, we love the P series. It's easy to work with. So it's a P series, and P equals 1/2. And so since it's a p-series with p equals 1/2, what can you tell me about this particular series?
It diverges.
It diverges. Okay, so we're saying all these black things that are below are diverging, i.e. they're headed towards infinity. So then we come to the unknown red, and we want to know, does it converge or diverge? And we notice that the red stuff is always above the black one. The black ones are going to infinity, so what can you tell me about the red ones? They must also be headed.
They also diverge?
Yeah, they're also headed towards infinity. They also diverge. So in this particular case, here's our, here are our B's. So this down below is the sum of our B's, and it diverges. And so we would say that the sum of our A's also diverges by the comparison test. And you might say, how do I know just from the symbols without the graph that the red one is above? Notice that we're subtracting in the denominator. So we're subtracting in the denominator, which makes our denominator smaller, and it makes the whole expression bigger. So subtraction in the denominator makes the whole expression bigger. Questions about this? Very good. All right. So in using the comparison test, we must, of course, have a known series, Bn, series of the Bn's, for the purpose of comparison. Most of the time, we will use one of these series, either the p-series, that's what we've just used, or the geometric series. So these are our friendly comparison tools. So let's do a first example of this. All right. So I want to know what's going on with the sum of the 1 over root n times 3 to the n's. If you look at the root n, you might think to yourself, hey, this might be a p-series because this might have a power of 1/2. Or if you look at the 3 to the n, you might think geometric series. But it's combining both of those terms. So this is neither a p-series nor a geometric series. So we need an idea. We need to compare to something. So what do you want to compare to?
Well, we only have geometry, right?
Sure. So we could compare to which series?
Geometric series?
And which geometric series? Actually, let me go back to the manipulates for a second, the interactive figures, and this might help you to see what's going on. So notice in the first case, or in this case, here we have a root k. We'd started with a root k minus 3, and so we replaced the root k minus 3 with a root k. Like there's this little complex piece and we're going, hey, in order to compare, let's just get rid of the thing that's making our lives miserable. Similarly, other example, we were given this 1 over k squared plus 10, and the plus 10 is complicated for us, and so we just got rid of it above, and we decided to compare to 1 over k squared. So you sort of take the complicated things out and compare to something that's known that is simpler. So with that in mind, let's go back to our question that we were working on. So is there something here that we could get rid of that would make things a lot clearer?
Could we make the 3 a 1 and then we just have 1 over root n? Can we do that?
Okay, so that would be one option. Okay. Let's see what happens. Okay. So if we compare to the sum from n equals 1 to infinity of 1 over root n, this is which kind of a series?
P series?
So this is a p series. And what's p?
1/2.
1/2. And so does this converge or diverge?
Diverge.
So it diverges. Good. Okay. So we want to compare to this series here, which diverges. That's great. We just need to verify one other thing. Since this one diverges, we need to make sure, we need to confirm that the 1 over root n's are less than or equal to the 1 over root n times 3 to the n. Because this one diverges. And so if we want to show that this one diverges using comparison test, we need this inequality to hold. So is this true? Is it true that...
Well, if the 3 has a scalar and an exponent, the denominator must be bigger, no?
So this would make, so that 3 to the 1 would be 3 to the 2 would be 9.
It's just less than. It is not less than equal, so it's just less than, I guess.
So which of these terms is smaller? The left or the right?
The left one. The left one is small. I mean the right one is smaller.
The right one is smaller.
Yeah, because it's in a denominator.
Yeah, because we have a much bigger denominator. So unfortunately, this inequality isn't true. And so what that tells us is that our comparison failed. So, or since we don't fail any longer because we're in America, the comparison has room for growth.
Other words for inconclusive?
No, this one isn't actually inconclusive. It just doesn't work because the inequality is just straight out doesn't hold. So what that means is we got to try a different thing to compare to. So let's try take 2. Okay, so what do you want to compare to? Take 2.
One over 3 square root of n, I guess.
1 over 3 what?
1 over 3 square root of n. That will be always greater than...
Like this?
Yeah, it will be always greater than 1 over square root of n, 3 to the n.
Okay, so this thing is always bigger than or equal to 1 over 3 to the n root n. Sorry, I reversed the sides. Okay. does this one on the left converge or diverge?
Oh, still it's inconclusive. So I guess we need to choose a smaller term, I guess.
This one diverges,
Mhm.
so this sort of didn't help us at all. It's inconclusive.
Oh, yeah.
Great. Okay. Take 3. What do you want to compare to?
1/3 to the n.
1/3 to the n. Thanks, Vu. Okay, so we compare to 1/3 to the n. So let's see. This would be the same thing as 1/3 to the n, which is which kind of series?
Harmonic?
Harmonic series would be 1/n.
P?
Symmetric.
It's a P series, right?
P series would have a number in the power.
Geometric.
Oh, I see.
Yeah, so it's like, so far we've got harmonic, no, that didn't work. P series,
Exponential
no.
series?
So it's a geometric series. So it's a geometric series with R equal to 1/3. So does it converge or diverge?
I think it converges.
Converges, good. Yay. So what do we have here? We have that the sum of 1/3 to the n from n equals 1 to infinity converges. And then we're comparing this to the sum of 1/√n times 3 to the n. Which direction does the inequality go? Which of these items is bigger?
Greater than equals to.
The left side is bigger, right?
Yep.
So the left side is bigger and converges. This must mean that the right side is smaller than a number, but bigger than 0. So that must mean that the right side also
Converges.
converges. So we could say this, we could state our conclusion as follows. We could say that the series from n equals 1 to infinity of 1/√n times 3 to the n converges by comparison to the convergent geometric series sum of 1/3 to the n. Wow. That took us 3 shots at it. I'm thinking that we went around and some of you are going, wait, why didn't that work? Why didn't that work? Like, where are we doing? What are we doing? Why are we doing this? Let me put you in breakout groups for a couple minutes to talk through what we've just done. And maybe that will help generate a couple of questions, maybe answer a few questions before we go and do another example. So welcome back, most everyone. So are there questions about what we just did? So what I've observed in teaching this class multiple times is that the comparison test isn't that difficult. You just have to figure out what to compare to. And one of the challenges seems to be recognizing what you've done. Like you do this work, but you sort of like don't know whether it's helpful. And as I was thinking about it in prep for class, I thought about the following table. So there's some known series that you're going to compare to. So in our case, we tried comparing to first the sum of the 1 over square root of n's, and then we also tried comparing to the sum of the 1 over 3n's or 1/3 n's. These were our known series. The top is a p-series, the bottom is a convergent series. And what happens is that if the known series, this one that we already know that we pick out, is bigger and converges, then the unknown converges. If the known series is smaller and the known series diverges, then the unknown diverges. In the case where the known series is smaller and converges, we get what some of your classmates already called an inconclusive result. If the known series is bigger and diverges, our test is again inconclusive.
So Dusty,
Go ahead.
so it is always beneficial to check the smaller term first and then the bigger term, right?
It's not really a smaller and a bigger. It's
I mean,
it's sort of a it's almost like you have to take a guess at what the answer is before you start. If you think that the answer is that it's going to diverge, then you're going to want to try to make this scenario happen. If you think that the answer is going to be that it's going to converge, then you're going to have to try to make this upper left-hand corner scenario happen. And so when, for example, when Melissa picked out the sum of the 1 over root n's, which is a divergent p-series, what she's saying is, hey, by picking a divergent p-series, she's saying, I want the to show that the actual series diverges. But what happened is it turned out that this thing was smaller, and so we ended up with an inconclusive result. Although we had a false thing written, but an inconclusive result. And then when we tried adding that 3 to the front, we still were in that same category. Then Vu switched us over and said, hey, why don't we try comparing to 1 over 3 to the n? 1 over 3 to the n is a convergent series, and it's bigger. And so we were able to say this one converges, it's bigger, therefore our unknown converges. So we got stuck in this corner a couple of times. So bigger and smaller isn't so much important unless it's paired with converge and diverge. So if you've got bigger, you're talking about converge. If you're talking smaller, then you're talking about diverge. Did that answer your question, Jay?
Yep, certainly. Thanks.
Very good. Very good. Other questions about this before we continue?
Is there an easy way to do it?
This is the easy way. I don't know if that helps. I think that what will happen is that as you get practice, you will start to recognize the possible things that you could compare to. And as you recognize the possible things you could compare to, you will also know what will converge and what will diverge. maybe let's go off script a little bit. So let me see if I can open up the homework for a second. See if this will work. So so this is an answer to Twee's question. And the question is really, how do you know what to compare to? So let me just walk you through my thought process kind of quickly. So in this case, case of question 9, that 4 is a little bit irrelevant. And so I would like to compare to 1 over k squared. In the second case, there's all of these extra terms that basically become not very important as k gets really large. And so again, I would like to compare to the sum of the k squareds over the k to the fourths, which would be the same thing as the sum of 1 over k squared. Tell me about these two things. These are both which kind of series?
P-series?
P-series, and do they converge or diverge?
Converge?
They're both convergent P-series. Somebody tell me, what should we compare 11 to?
1 over k.
1 over k, which is what?
It's a constant.
It's a p-series.
It's a P-series with p equals 1. This is actually the harmonic series right here. So this one diverges as well. So these ones converge, diverge. It's the harmonic series. What do you want to compare 12 to?
I have a question.
Go ahead.
So if this 1 over k is a harmonic series, isn't the harmonic series the one that goes from plus minus?
That would be the alternating harmonic series.
Okay, thank you.
Yeah.
12 diverges.
Say again on 12?
12 diverges harmonic.
Yeah, it's the same thing as up above, right? How about 13?
Power series.
And or we'd call it a P series, but because the power series usually refers to X, but we think about that P as referring to power. What's the power?
3 over 2.
3 over 2. So does it converge or diverge? It converges.
Yep.
It converges.
P is greater.
Okay. How about 14?
1 over 5 to the k.
Yeah. 1 over 5 to the k.
Geometric.
This is geometric. And does it converge or diverge?
Converge, doesn't it?
Converge. This is like the same thing as 1 over 5
plus 1 over 20
to the k. So your R is equal to 1/5. Is this helpful?
Yes.
Yeah, a lot. Okay. How about this one right here?
4 over 5 to the k.
Yeah. 4 over 5 to the k.
And it's still a geometric series.
It's geometric. Does it converge or diverge? Converges because R is between -1 and 1.
Yeah.
Exactly. Okay. So then so far so good on all this stuff over here. So let's ramp this up a notch and think about the table that we've got, where we've got bigger and we've got smaller, and so this is all for our known, and we've got that they converge or they diverge. And so if the known is bigger and converges, then the unknown also converges, right? And if the known is smaller and diverges, then the unknown
lay down.
Diverges, right? But then we also have, ooh, I don't like that color. We also have these two possibilities that are inconclusive. Okay, so let's think about these various options and figure out whether this test is going to work. So on question number 9, we're going to compare to 1 over k squared. So this, what we're saying is that this part right here, this is our known. Does it converge or diverge? It converges. So since it converges, we're hoping that we live in this box right here, the known converge box, or the converge and big box. So let's just verify, is this known series bigger than or smaller than 1 over k squared plus 4?
Bigger than.
Bigger than. And how come? How do you know that?
That denominator has a +4, so it would get, the denominator would increase, so then the whole value would be smaller.
Yeah, so the denominator here is bigger, so the whole quantity is smaller, exactly like Enrique said. So this tells us that our known series is bigger than the unknown one. So bigger, it converges. Therefore, in 9, it's going to converge by the comparison test. Okay. Let's jump forward to 14 here. Okay. So we're comparing to this geometric series. Does the geometric series converge or diverge? Is this thing, it converges, yay. So it converges. Okay. And is the convergent series that we know, is it bigger than or smaller than the unknown?
Smaller.
Sorry. Is the known bigger or is the known smaller? So here's the one we know.
Known is bigger.
So the known is bigger. Why is the known bigger? Because we've got an addition in the denominator that's making this whole fraction smaller. So the known is bigger. The known converges. So yay, we're in the happy box. So our unknown must converge by the comparison test. Let's look at one more example and we'll call it good for the day. 15. So here, the known converges. Is the known bigger or smaller than the unknown series?
Smaller.
Smaller, right? Here, the unknown, the one we're trying to figure out, has subtraction in the denominator. So that means smaller denominators mean bigger fractions. So this is bigger. This guy is bigger. Or the known one is smaller, depending on how you want to, which perspective you want. And so we're on the small side. But our known converges. And so sadly, our comparison test is inconclusive. Comparison test is inconclusive, which is disappointing. And so when we come together again tomorrow on this, what we will do is we'll do a little bit more practice with the comparison test, but we will also talk about a more powerful version of this called the limit comparison test that gets rid of these terrible inconclusive options and is easier to work with. So the limit comparison test is more powerful, easier to work with. The only catch with that Saturday lecture is that Saturday lecture will be less intuitive. So thanks, guys. I appreciate all that. So thanks, everyone. I hope that you all have a little bit of a better idea of what's going on with these comparison tests. We will spend some more time on this on Tuesday, not Saturday, not Monday. In the meantime, please make sure to be working away at your homework. Be looking for the assessment. I have not posted the assessment yet today, but we'll do so by 5. And make sure that you sign up for your presentation slots as well. So have a wonderful day, everyone. And I look forward to seeing you all next time.